An electric motor converts electrical energy into kinetic energy. I am going to demonstrate a simple linear electric motor. I've taken some bare copper wire and I've wound a coil, and if we go to the left hand side here and look down the coil, the windings will go counterclockwise as they go away from us. I've also taken a battery and attached a magnet to each end. And the magnet at each end is actually two magnets put together, but we can think of it as one magnet. Here's a schematic of my battery and two magnets. The battery is arranged such that the left side is the positive terminal, and the magnets are attached such as the magnet on the right has the north pole on the right side, and the magnet on the left has the north pole on the left side. Now I'm going to take the battery and magnets and insert them in the left-hand side of the coil. I've used a PVC tube as a form to wind a longer coil, so now let me take the coil off the tube. Now I'll insert our battery magnet combination into our longer coil here. To explain what is happening here will require many of the topics we've discussed during the semester so far. Let's look at a cross-section through our coil. So think of taking a cut along a line down the axis of our coil. So this would be that cross-section, and so the battery and magnet would be sitting inside the coil like this. So here's a schematic of that cross section with the battery sitting inside the coil. The battery will be making electrical contact to the coil through the magnets, so current will only be flowing in the coil in the region here between the magnets. And since the coil is wound counterclockwise, if you're looking from the left-hand edge down the coil, the current will be flowing out of the page in the bottom here, which I'll represent with dots. And the current will be flowing into the page in the top here, which I'll represent with crosses. So only in the region where the magnet and batteries are sitting will there be a current flowing, and so in this region, this flowing current will generate a magnetic field. So the generated magnetic field will look something like this. So only in the region where the battery and magnets are is there current flowing, and so only in that region of the coil will there be a magnetic field. It is the interaction of the magnetic field from the coil and the magnets that propels the magnets and battery down the coil. Now let's focus on one of these magnets. Here's a close-up of our magnet on the left. Now, currents cause magnetic fields. In a magnet, it is bound currents that cause the magnetic field. The bound currents are due to the electrons going around in orbits and electrons spinning. Now, each of these circles represents the bound current associated with an atom. So you can see that on the interior of the magnet, the bound currents for adjacent atoms are going in opposite directions, so they will cancel. But there won't be a cancellation on the outside perimeter because there's no adjacent bound current to cancel. And so we can represent a magnet as a bound current that's going around the perimeter of the magnet. So for our magnet on the left, the bound currents will look like shown in this illustration, setting up the North Pole here on the left and the South Pole on the right. Looking at our battery and magnets inside the coil, for the magnet on the left, those bound currents will be coming out of the page on the bottom here, going around the magnet and then into the page in the top. And since the magnet on the right is flipped, the bound currents are going to be coming out of the page along the top, around the magnet, and then into the page along the bottom. Looking at a current element, that is a current flowing through a small differential length dl, the force on that current element is given by IdL cross with the magnetic flux density field. So we're going to use this equation to understand the net forces on the magnets that propel the battery-magnet combination down the coil. So if we look at, say, a current element right here, the current element is coming out of the page, and the magnetic flux density at that field will be a tangent to this magnetic field line, so B would look something like this. And if we take the cross product between IdL coming out of the page and that magnetic flux density field, we'd get a force pointing down to the right, something like that. Now looking at this current element right here, the magnetic flux density field will be pointing tangent to the flux line here where the current element is. The current element IdL is pointing into the page, so when you take IdL cross B, you get a force upward to the right. And so the sum of those two forces is a net force to the right. And you can think of any combination of current elements for all the current elements around the perimeter, and they would all behave the same way, giving this net force to the right. We can apply similar reasoning to the magnet on the left. So at, say, this current element, the magnetic flux points like this, a tangent to our magnetic flux line. The current element is into the page, so when we take IdL cross B, you would get a force upward to the right. Now if we take a current element down on the bottom here, the magnetic flux density field at this point would be pointing tangent to the flux line through that current element. The current element is coming out of the page, so IdL cross B on that current element would be a force pointing down to the right. So the sum of these two forces will be a net force to the right. And again, you can think of any combination of current elements and account for all of them around the perimeter of your magnet, and the net result is a total force to the right.